We are starting over with ECE 442-542. We'll see if we get any further this time. Maybe we will, maybe we won't. But this time I actually read the error log. Last time I just went ahead and didn't read it. Now I'm a little more nervous than the previous time. But homework number 5 is due today. Homework number 6 is due a week from today. And project deliverable number 1 for 542 is due today. We'll have a review session a week from today, and exam number 3 is a week from Wednesday. Just as a reminder, there are additional material and videos available to supplement Unit 5, and those are listed here on the right on the screen. And today what we want to do is get into the PID controller. And we'll quickly summarize that, and we'll start working through one particular illustration of that, which is the P part, the proportional controller. And you might have actually seen that in one of your problem solutions using the Ragazzini design. You might have ended up with a proportional controller, your C of Z being just a constant. But we'll talk about the stability range. What are the limits on on K? Can we adjust that K as the way we want arbitrarily, or are there restrictions on some interval of K that actually causes or allows the system to be stable? And then we'll start looking at some root locus properties, and they all arise by simply examining the denominator polynomial, the characteristic polynomial, creating a characteristic equation from that, the 1 plus K, and here G is overbarred. That G overbar means it's the series combination of the original plant G with the controller C. So all of that is what I'm referring to as G bar. We'll see that these, looking at this expression, 1 plus K G bar of Z equals 0, leads to really two different conditions. A magnitude condition, which says that the absolute value or the magnitude of K times G bar is equal to 1. And it gives us a phase condition when we assume that the gain K is positive and we have negative output feedback. We will see that the angle on that G bar of Z is equal to minus 180 degrees. Those two conditions actually drive everything on our root locus construction. And if you want to read up on the root locus construction and design, that's in chapters 13 and 14 of the Shams outline, which you should have access to through the U of A library. Let's summarize what this PID controller looks like. And one intuitive way to think about the PID controller is the PID is made up of 3 different sort of sections or 3 different parts: a proportional piece, an integral piece, and a derivative piece, and that's where the P, the I, and the D come from. The proportion, and if you wanted to, you could start erasing or not having some of these pieces in your PID controller. If you simply wanted a proportional controller, you wouldn't have these 2 other parallel paths, the integral path and the derivative path. But whatever that path is, that's really what it's doing to the air signal E of t. Is it simply scaling the air at the present time and injecting that as a part of the input U? Here is our U of t going into the plant, and it's made up of 3 different pieces. One piece is proportional to the air, one piece is an integral of the air, and you can see then that if the air is non-zero, the integral of that could be growing. So you could have some term that's actually getting bigger, even though the air actually might be getting smaller, because you're now adding, continuing to add that particular component due to an error signal. And the derivative term now is responding to the rate of change of the error signal. You have those three pieces, and here is another way of thinking about that PID controller. Let's just assume we have a hypothetical error signal that I'm indicating as this blue waveform, and it's decreasing with time. And let's just draw a line in the sand and say that's the present time, t sub 0. Whatever the error signal is at t naught at now, that's going to be scaled by the proportional piece of our PID controller. The error before that, the error in the past, has now already been integrated up in that integral term. And so the integral part of your PID controller is actually concerned with the past behavior of your error. And the future is now the part that's going to be looked at or thought about relative to the derivative term. Because it's the slope, it's sort of saying, oh, I'm going this direction, I'm going that direction. The derivative piece now tells us or responds to future error behavior. And you can sort of see then that the I and the D term have a trade-off kind of relationship. If you emphasize the integral piece, then maybe you're more concerned about steady state accuracy. You're trying to now worry about the overall behavior in the steady state. And that would then be, oh, now maybe I want to just have concern with the steady state accuracy. Maybe I just use a PI controller. Or if you're interested in moving or modifying the dynamic behavior or adjusting the transient behavior of your closed loop system, you might want to think about what the derivative action is doing, and that's now the speed of response. And in control, you always have this trade-off. How much am I emphasizing the steady state accuracy, and how much am I emphasizing the speed of the response? That's sort of a very overview way of thinking about a PID controller. Let's now get into the beginning piece, and by beginning I'm saying now we're working through the spelling of PID, and let's just concentrate on the first letter, the P part, the proportional part. Proportional controller just means that this capital C of Z, this transfer function, is just a gain K. So C of Z is equal to K. And if we plugged that K into our controller transfer function in the closed loop system, this is the picture that we would have. We now have our plant G of Z, and you know how to come up with a G of Z. You start with either a difference equation and find the transfer function of that difference equation. Maybe you've done a zero order hold equivalent of an analog system dynamics. You somehow have created this G of Z. Now we want to investigate what can we do when we apply a proportional controller to that particular system. This should just be a review. The external transfer function, or the transfer function between the reference input R and the output Y, you should be able to derive that if you want to, but that's now CG over 1 plus CG, and I'm explicitly substituting K, that proportional piece, for my controller transfer function C. This is now KG over 1 plus KG. Now, if this is true, if this is our closed loop transfer function, T sub C of Z, what's influencing in that expression, in that transfer function, what governs the closed loop dynamics? What do we want to think about or concentrate on or focus on if we're interested in the closed loop dynamic behavior of that system. So we now have our plant G of Z. What's going to give us our closed loop dynamics? G of Z is the plant. It has open loop dynamics. We now have applied a controller to that, K, and we've put it in a closed loop configuration. What do you examine in this transfer function to try to understand how it's going to behave in the closed loop? The poles of that transfer function. And what's going to give us the poles? Well, if we focus on the denominator expression, that's going to give us that's going to tell us what the dynamics are doing. In this case, I was looking for an answer of 1 plus k g of s, the denominator expression. That's what governs the dynamics. Let's look at a particular example, and let's go ahead and assume a proportional controller, and our example now is a single pole. What can you tell me about that pole before we go too much further, that system before we go too much further, the G of Z system? It's unstable, isn't it? We have a pole outside the unit circle. If somebody kicked this system, what would happen to the output? If you applied a constant input to this system, what would happen at the output in the open loop? Or what's the mode of the behavior of this system in the open loop? How will it behave? Do you see what it might contain? You just told me where the pole was in the open loop. It's at 2. So now you have 2 to the n is what's governing for non-negative values of n. That's governing the behavior of your system. You have 2 to the n, and that's just blowing up. That's going unbounded. So we probably don't want that type of behavior. We're then going to try to control that system. We put a constant controller into that controller's location, and we simply plug in the appropriate terms and see what happens. In this case, we have CG over 1 plus CG. If we replace C of Z with this proportional controller, just K, that's as complicated as the controller is going to be, then we have kg over 1 plus kg. And let's now replace g with what we said we were working with, which was 1 over z minus 2. Plugging that in everywhere where g is, we have k over z minus 2 all over another rational expression, 1 plus k over z minus 2. Now we have a ratio of ratios. And that's maybe making us a little nervous, so let's clean that up. If we put everything over a common denominator, which is z minus 2, now we have a numerator and a denominator ratio which have share a common denominator. That can be canceled. And we're left now with our closed loop transfer function equaling capital T sub C of Z equal k over z minus 2 plus k. So now, based on what we have looked at before or talked about just a minute ago, we want to look at the poles of the closed loop system, and that's going to govern our closed loop dynamics. And what does that mean? Well, the denominator now is z minus 2 plus k. This is our closed loop polynomial. And if we set that equal to 0, then that gives us our characteristic equation. which the values of z that cause that to be true will be the poles of our closed loop system. This is now our characteristic equation, and maybe I should say closed loop characteristic equation. It's the characteristic equation of our closed loop system. What's one goal that we might have if this is now the controlled system? We now can select K. How would we maybe want to select K? What's our goal, or what is one goal that we might have? Pardon? So now we could make K is our adjustable parameter. We can make it whatever we want, right? And what do we want? Well, that's maybe up to us. That may be up to us. It may be up to our boss. It may be up to somebody else. So let's state for a goal that we want to adjust K, this controller value, adjust K to locate the closed loop pole at, I'll be somewhat vague, at an acceptable location. There's our closed loop characteristic polynomial. Now we can solve that for z if we wanted to, and actually observe that whatever we pick for k, that's what our mode will be, whatever results for z. And we might have an idea as to what we want to do with that decision on k. If we simply look at the z-plane, we might want to be thinking about what's happening as we adjust k versus this unit circle. What's special about the unit circle? Why do we even worry about the unit circle? That's probably where we want all of our closed loop poles. That is where we want all of our closed loop poles in our system. We're starting now, though, with a pole, and we'll represent poles as x's and zeros as circles, open circles. We're now starting our system behavior at a pole located at 2. So this is our open loop pole. If we didn't do anything to that system, if we just had g of z, then we would be stuck at that pole at 2. And we know that that's not going to give us acceptable behavior. What's going to happen as I look at positive values for k? What happens to z? If I picked k equal to 1/2, what's z going to be? It's going to be right here, isn't it? 1.5. If this was k equal to 1/2, if I said k equal to 1, now I'm right here. If I said k equal 3/2, I'm right here. K equal to 2, I'm right there. Do you see that I'm actually able to put my closed loop poles anywhere I want on this line starting at 2 and going all the way to minus infinity, we could say that this is now the locus of potential closed-loop poles for k greater than or equal to 0, what I've indicated in red. And we might actually just put an arrow on that. And in fact, that red line is the root locus for this particular system. Hint, hint. So now you've drawn a root locus without even realizing it. That's the easiest root locus we can draw, and that's with a one-pole system with positive or non-negative k. It's going to be to the left of that pole. We've already looked at some potential values for k. We probably don't want a k equal to 1/2, do we? That makes our system a little better, but it's still unstable, because that puts us at a z value of 1.5. Let's look at some possibilities. Well, let's just look at one for now. One possibility for k. Here is our closed-loop polynomial. What if somebody said, you know what, I want that to be z minus 1/2. This is now what I will call the desired closed-loop polynomial. So I have an expression, it's first order, and now I say I want to pick a first order transfer or a first order polynomial, and I want that to have a root at z equal to 1/2. And that would be then expressed as this polynomial z minus 1/2. This is another way of thinking about what we're doing. We already demonstrated just picking k's and seeing how that marched along that red line. Here's another way. Now you say, oh, you're going to give me a desired closed-loop polynomial. Let me set that equal to my actual closed-loop polynomial in terms of the unknown k, and let me solve for k. That's all we're doing in this example. And the way that we can now solve for k, although you already know what k is based on the previous thinking process, but making this more of a procedure, now we can say, well, let's just equate the coefficients on both the left-hand side and the right-hand side and solve for the unknowns. In this case, we only have one unknown, but in general, we might have more. So equating coefficients on both sides. If I looked at the coefficient that's scaling z, what's the coefficient of z on the left? 1. What's the coefficient of z on the right? 1. So that was trivial, wasn't it? That didn't really give us any information. So a lot of times you might not even see that discussed. They might just immediately jump to this equation and not even tell you that this equation came by comparing coefficients. They may say, obviously, minus 2 plus k is equal to minus 1/2. Or they might say it's immediately clear that minus 2 plus k is equal to minus 1/2, depending on what you're reading. But we can now solve that for k. K is now equal to minus 1/2 plus 2, or 3/2, and that's what we had already determined. That if we cranked up that knob, k, from nothing all the way up to 3/2, we would push that closed loop pole into the unit circle and locate it right at 1/2, z equal to 1/2. Which says then that, and what was K? K is a proportional controller, one little subset of a PID controller. With K equal to 3/2, the closed loop transfer function becomes, and we already had that T sub C of Z somewhere written, there it is, K over Z minus 2 plus K. We can now substitute that K in, and now we know what our closed loop transfer function is. Our closed loop transfer function now is T sub C of Z equaling K, which is 3/2 over Z minus 2 plus 3/2, or 3/2 over Z minus 1/2. So for a constant controller, a controller of 1.5, we now have stabilized this unstable system. Let's make some observations relative to this proportional controller, this P controller. 1, the controller C of Z, did it cancel any poles or zeros? If we looked at the block diagram, did I sketch a block diagram right here? If you plug in 1 over Z minus 2 into G of Z, did that K cancel anything? No, we sure wouldn't want it to cancel the pole, would we? That would cost you 120 points on a 25-point problem. Not a good choice. So here, C of Z does not cancel any unstable poles or zeros to produce that T sub C of Z of 3/2 over Z minus 1/2. That's one observation. Second observation is the closed loop system is now stable with one pole, with a single pole at Z equal to 1/2. If somebody said, well, what's the output going to look like due to an initial condition now in this closed loop configuration? What's the structure of the initial condition response? Can you tell them? Where's your closed loop pole? It's at 1/2. What does a pole at 1/2 tell you? Does that tell you anything about the way that system's going to shake? So that pole tells you the mode, doesn't it? That's the structure. So it's going to shake. It's really not shaking, is it? It's real, so it's just going to exponentially decay at 1/2. 1/2, 1/2 squared, 1/2 cubed. So it's just going 1/2, 1/4, 1/8. It's just collapsing. It's exponential behavior, and that's what the initial condition response would be in that closed loop system. So if somebody now has this system and it's closed loop and they walk up and kick it, it's just going to exponentially decay from that initial condition. Whatever that impulse or pulse established for initial conditions. This would then say alpha 1/2 to the n could be then the structure of the response. And maybe that's comforting. Maybe that makes you feel good. Now you say, oh, if this does get excited, then I'm going to exponentially decay. Question? So now the question was, what did you apply as an input? I didn't apply an input. I just said somebody went up and kicked my system and sort of or they went up and somehow this system started to possess an initial condition. So I didn't have an explicit input, is what I was assuming. But if you did have an input, then you would not only have this mode, but you would also have the structure due to the input that you might apply as the reference input. So this is just the initial condition response. This is just sort of how this system would respond if you now had non-zero initial conditions on this closed loop system. Now, if you did apply an input, let's say you applied a constant for your reference input, you might be wondering, what's the DC gain of this system? How is that going to adjust what I inject in as a constant input? That's our third observation. The DC gain of our closed loop system. And you now know how to find that. That's evaluating T sub c of z, our closed loop transfer function, at what value of z? At 1. In this case, then, we have 3/2 over z minus 1/2 evaluated at z equal to 1. Our DC gain is 3. And now you might say, well, what does that mean? Well, let's look at what happens to our system as far as its steady state error if we apply a unit step to this closed loop system. Our steady state error due to a unit step. What's R look like for all time if we are applying a unit step? What's R of n? It's 1 for all n, isn't it? So R at infinity is 1. Can we even talk about a steady state output? Does that make sense to talk about a steady state output in this case? And if you're shaking your head yes, why? Not the output y, but WHY, question mark. Why is it okay to talk about a steady state output? The system is stable, isn't it? Since our system is stable, if we excite it with a constant, it's going to exponentially go to a constant value. What will that constant value be? What is y at infinity? I'm assuming the transients have all disappeared. Is it somewhere here? Information that might help us determine what the output is going to be in the steady state given an input of 1. It's going to be 3, isn't it? That's the DC gain. That's how a constant is scaled. If I put in a 2, I would go to 3 times 2, or 6. If I put in a 1, I'm going to 3 times 1. So my steady state output, y of infinity, is 3 times 1, or 3. I put in a 1, I get out a 3. I'd love that if that was my bank account, right? I put in $1 and I get 3 out. But this is now a dynamical, well, I guess your bank account could be considered a dynamical system, but this is probably some other kind of system. What's the steady state error? That's now r of infinity minus y of infinity. That's the output of that summing junction in our closed loop block diagram in the steady state. And that's now 1 minus 3, or minus 2. This is what we have in terms of a picture, if you want to sketch that. Here is where we wanted to go. This is, let's say, 1. That was our step input, and that started at time 0. And what did our output do? It had an exponential behavior. It was first order. And it went up to 3. Our steady state error is right there. The difference between where we wanted to go, a value of 1, and where we actually went, 3. And you may or may not be okay with that steady state error. That's something that you might have to trade off. So in this case, how did we achieve this behavior? This was achieved using what kind of a controller? A proportional, a P controller. If we're not happy with this, maybe we need to change controller structure. Maybe we need to look at a different controller. Therefore, we may need a different controller structure. Or what this is telling us is that using a proportional control strategy may not produce an acceptable steady state error. Even though we might have been happy with the transient. And what are we seeing? We're seeing a trade-off between steady state error or steady state accuracy and the transient response. Before we go too much, well, let's go back here somewhere. And look at what we did. We actually pushed that knob, K, we cranked it up from 0 all the way up to 3/2, and we moved into the unit circle, which was good, and we moved into a value of z equal to 1/2 for our closed loop behavior. Let's look at what we can do with this K, or let's adjust K and see what can be achieved relative to maybe being available to us from just this proportional controller. Let's examine adjusting K a little more before we talk about a more complicated controller structure. We could increase K to yield a deadbeat response. And you now know how to do that. There's our controlled closed-loop characteristic polynomial. If we want deadbeat response, what would we set that equal to? We would set K equal to 2, wouldn't we? The polynomial would be z minus 0. We want the root to be at 0. Here's our desired pole is at the origin. And if we compare then the coefficients, let's not worry about the coefficient of z since that's trivial. This now says that we have minus 2 plus k equaling 0, or what you have already told me, k equaling 2. So that now what's our controller? It's a proportional controller. C of z is k, and that's now 2. And what's our closed loop transfer function? That structure hasn't changed. That was still k over z minus 2 plus k, or that's now 2 over z. What does this give us if you wanted to look at the steady state behavior? What's the DC gain here? Now we put in a 1, what do we get out? A 2. Maybe that's better than what we had when we put in a 1 and got out a 3. We've cranked up the gain and now maybe improved even the transient, the speed of our response, and the steady state accuracy. Using exactly the same controller structure. We're still using a proportional controller, but we can achieve different behavior with that same controller structure. And that's what we want to start thinking about, is what are the possibilities, what are our options for adjusting this one knob, just the proportional knob in a controller? Does that produce or provide us with different possibilities? And in this case, it does. Is there a limiting value? Can we just keep cranking up the gain k and just get better and better? So we do have limiting values, and somebody's already way ahead and said that the limiting values are 1 and 3. Where did that come from? It came from the root locus, which I know is what was being envisioned. You're just going to start dreaming about root loci because they're beautiful. They're patterns of what? What are the root loci? What was this root locus for this sort of simple system? It was just that red segment of the real line. That's the root locus for this particular system. And it gives us It gives us all the possible values of our closed loop poles by adjusting that one knob K from 0 all the way up to infinity. And obviously, in a digital control environment, we don't want to crank that up very far. We want to crank it what? Just far enough to get us to the unit circle. That's the lower limit. And then we can crank it up even more until what? Till we just start to exit the unit circle, and that's the upper limit on the adjustment for K. So this knob that we have the ability to go from 0 all the way up to infinity, we probably have a sweet spot. There's a Goldilocks region on that knob. And we can only go from the lower limit to the upper limit if that knob is being adjusted for stability purposes. That's what I want to now just try to write down. And really, I'm wanting to answer, although you're way ahead of me, is there a limiting value of K for stability? And I've already given you the answer, so let's just write that down. Is there a limiting value of this adjustable parameter K for stability? And hopefully, if what I was saying before didn't make sense, now maybe it will. Here's our z-plane. We start there, and we've learned that with non-negative values of K from 0 all the way up to infinity, we can push this pole wherever we want between 2 and minus infinity. That's our flexibility on that knob K. And what we want to examine now are two possibilities. We have the value of K to get us to that triangle and the value of K to get us to minus 1, and those are our limits on K. So I will say that this location, the triangle location, is the lower limit for the z-plane location, because that gets us right on the boundary of stability, right to the unit circle. And this point at minus 1 is our upper limit. And we can, and this is actually our root locus, that red locus of points. The lower limit is when z minus 2 plus k is actually equal to z minus 1. We needed a pole at 1, or the value of z equal to 1 will cause that to vanish. Comparing coefficients or constants, we can see then that k is equal to minus 1 plus 2, or 1. So our lower limit on k is 1. If that knob was labeled, we would want to be beyond 1. And the upper limit which I've indicated by a box, is now when z minus 2 plus k is equal to z plus 1, or when z is equal to minus 1, that will vanish, that polynomial. And that now says that k is equal to 1 plus 2, or 3. And now we've actually derived or convinced ourselves that for stability, we want K to be between 1 and 3. Why did I not put equalities on those inequalities? Isn't it okay to be right on the stability border? If I'm talking bounded input, bounded output stability, the answer is no. Because if I was right at z equal to 1, I could put in a constant, and what's going to happen? I'm going to actually go as a ramp. I'm going to go as n. If you wanted to look at z over z minus 1 hit by something z over z minus 1, I now have a z minus 1 squared in the denominator, and if you look at the table of z transforms, that corresponds to a ramp. So for bounded input, bounded output stability, I need to have strict inequalities for stability. So you hope that on the third exam and the final, these root loci are that easy to draw. A standard root locus is given by what? The roots of 1 plus k g bar of z equaling 0, where this g bar is this series combination or cascade of the controller structure, C of z, with the plant, G of z. The root locus is given by the roots of that equation, the values of z that cause that to vanish, as k is increased from k equal to 0 all the way up to positive infinity. And one of the features that made that previous example so straightforward was the fact of that system wasn't very complicated. It was first order. We just had one pole. How many finite zeros did we have? We didn't have any, did we? So we just had one singularity to worry about, and that was the pole at 2. So let's look at a second example and see if everything is that easy. Example 2. Suppose that g of z is now equal to 1 over z times the factor z minus 3 halves. And let's again just assume that our controller is a proportional controller. And now what we want to, so before we even go any further, do you already start to see what kind of natural behavior this system would exhibit if we didn't put any control around it, if we just put some initial conditions on this in an open loop configuration? What would happen? One pole is outside the unit circle, and all it takes is how many poles for things to go bad? Just takes one. So that one pole at 3 halves, or 1 1/2, is causing problems. So we have an unstable open loop system. Can we actually stabilize it with a proportional gain, k? Or we learned in the previous example that we had a range for stability of k. Can we find such a range for this problem or for this example? Is there a stabilizing value or range of stability, or should say a range of stabilizing values for K. If we're interested in closed loop stability, what's the figure that you might be seeing now in terms of what we're talking about? Block diagram. What kind of block diagram do you see if we now have a closed loop system? Here's G of Z, and we know what that was. That was 1 over Z times Z minus 3/2. We're using a proportional controller. That's now here. And we now know how to measure the output, feed it back, compare it to the reference, and let that error signal drive the controller. The controller now is proportional. It just takes that error and scales it and then injects that into the input of our plant, of our system. That's the block diagram that you see for a closed loop interconnected system with a proportional controller. What's the closed loop transfer function? If you wanted 1 point out of 50 on a test, you might say, well, that's y over r, of course. But then you can actually derive that, can't you? Or you can just write it down. It's probably on your crib sheet, and now it's CG over 1 plus CG for negative unity output feedback, and that's now KG of Z over 1 plus K G of Z. We want to know, for stability purposes, is there a range of K, and it's now in the denominator of that closed loop transfer function. What's the range of K for all roots of 1 plus K G of Z equaling 0 to lie inside the unit circle? That's the stability. We want to know, is there a sweet spot? Is there a range on K that will allow, how many closed loop poles do we have? How many open loop poles did we have? How many open loop poles do we have? And it doesn't take too many hands to show me the answer. If you give me 2 hands, that's okay as long as you don't show me any, or just 1 digit on each hand, right? So there's 2 open loop poles. How many closed loop poles? What's my controller structure? Did I add any poles with my controller? No, so I actually now just have 2 closed loop poles. For stability, I want to know, is there a value of K or range of K that will allow both of those poles to be inside the unit circle? You know where the 2 poles are starting. One starting at the origin, that's okay. One starting at 3/2. Do they just go away from each other? Do they kind of feel like they want to come together? What's this dynamic between these poles? Well, that's determined by this characteristic equation. 1 plus kg of z equaling 0. So the root locus of g of z is actually what we're after. And that is 1 plus k g of z equal to 0. We want to find the values of k that satisfy this equation. That will give us all the red branches. So I have two closed loop poles. That means I really have two red branches, and they may be on the same line segment, and so it may be difficult to say, well, I thought you said there were two. I just see one segment. Well, that one segment might have two branches described by that one segment on the real line. If somebody takes this and isolates k and g of z, what do you have? Or, said another way, can I subtract 1 from both sides of that equation? The answer is yes. That's just like adding 0. So I can add 0 as much as I want, and if I do that, I now see that k, g of z, is equal to minus 1. That shouldn't be any different than this black equation. 1 plus k g of z equal to 0 is the same as k g of z equaling minus 1. But we are all electrical engineers. And what do we see when we see minus 1? Do you see the polar form of that? Oh, what's the magnitude of that minus 1? 1. What's the angle of that minus 1? 180. So this is another way, and I'm going to be kind of cute and just say, oh, it's minus 180. If I have minus 1, do you see that I can get to minus 1 either going through plus 180 degrees or minus 180 degrees? It just makes more sense to talk about minus because that kind of seems like a delay. In the analog setting, that's true. That's why it could be plus 180, but the convention is it's minus 180. So I now have this kg of z, and if I plug in any z, give me a z, any z, what can that z be? It can be anywhere on that complex plane. And what will that do? What will kg of z be? What will kg of z be? It could be complex, couldn't it? If z is complex, if I plugged in a complex number for z into this g of z expression, could I not come up with a complex number? Yeah. Why not? So this number right here, kg of z, can be complex, but what is that number? Well, it has to have a magnitude of 1, and it has to have an angle of minus 180, or it doesn't satisfy this black equation. So we're looking at all of the k's such that the magnitude of kg is 1. So we have this wide two-dimensional z-plane. We want to shade in red the values of z that satisfy this equation. We want to know what are the values of k such that kg of z has a magnitude of 1 and has an angle of minus 180. And that will then be all of the k's that satisfy this 1 plus kg of z equal to 0. And then what do we want? We hope we hope that two of those red branches simultaneously are inside the unit circle. If they are not, then we can't stabilize this system with a proportional controller. First thing we want to do if we sketch the root locus is we're really asking, when is this expression, this kg of z, for what values of z does it have a magnitude of 1 and a phase of minus 180? And what we're going to do is we're just going to concentrate on g of z and say, when does it have an angle of minus 180, and then adjust the k to give us the magnitude of 1. And that's how we'll play. So now all the points in the z-plane such that g of z has an angle of minus 180, those live on the root locus. And we sure hope that two of those branches of the root locus are inside the unit circle simultaneously. Then we find the k that allows that to happen. Do you see that? Well, if k is greater than or equal to 0, then the angle of kg of z is equal to what? What's the angle of k if k is greater than or equal to 0? It's 0, isn't it? It's not adding anything, so this is now just the angle of g of z. And we now want to know what are the poles if k is non-negative, if it's greater than or equal to 0, then the angle, the phase of kg of z is equal to the phase of g, has to equal minus 180. On the root locus. So, what does this root locus look like? Here's the z-plane. And how do we sketch the root locus? To start, it's really pretty easy. We just first put down the x's and o's. The x's are all the open loop poles. The zeros, or open circles, are all of the open loop zeros. Finite. Where were my open loop poles in this transfer function? 0 and 3/2. So I put two x's on my z-plane. One is at the origin, and the other one is at 3/2. Did I have any finite zeros? No. So I don't have to put any open circles. Now, what I want to do is examine some points on the, well, yeah, let me look at some points. So now I'm going to get very artistic. Suppose that I put something over here, and there's a star. So let me just play right now on the real line and see if you can answer some questions. Let me put a box here. And since everybody's going to the cloud, let's just go ahead and put a cloud over there. So now we have stars, boxes. I guess a box you don't see in the sky. Maybe I should have put a moon. Anyway, so we have a star, we have a cloud, and we have a box. And I want you to tell me which of those belong on the root locus. So which points star, box, or cloud, or all, lie on the root locus? Now, how in the world are we going to figure that out? Well, let's just ask the question. Suppose we wanted to know what's the angle of g of z when Z is at star. So now, what do? We have poles and zeros. We have open loop poles and zeros. We don't have any zeros, so we don't really even need to worry about their contribution to the angle or the phase of G. But what do? Well, we stand at this pole at 3/2 and we look to our right. And we say, what angle do I need to make to look to the star? There's star, and what angle do I need to... Now I hate that I can't show you this at home, but stand up if you're at home, put your arms out, and say, okay, I'm putting my right arm out. That is my right, yeah. Okay, my right arm, and I'm looking to the right, and now I want to try to look and see what angle I'm making to see star. What's that angle? I didn't have any zeros, so let me say here are my zeros. They didn't even exist. There were no angles associated with the zeros, but the poles are in the denominator, and they contribute negatively, or I subtract those. And what was the angle due to the pole at 3/2? 0. If I'm now standing at the origin, the pole at the origin, and I look to the star, what's the angle? If I look from the origin to star, what's the angle that I form? 0. So I now have my angles due to the zeros, which didn't exist, minus all of my pole angles, and what's the net angle? Is that equal to minus 180 or plus 180? No. So that star can't be on the root locus, can it? So this is a no. Star is not on the root locus. What about if we evaluate the angle of G when Z is equal to the box? We don't have any zeros, do we? So now I'm at 3/2. This is going to be hard, but I'm now, relative to the positive real line, I now need to turn and look, I'm going to cramp here, to what? The box. What angle did I have to look through to go from measuring at 3/2 to look to the box? Let's go positive up. So now I had to go through 180 degrees. So that was 180 degrees. Now I'm standing at the other pole, which is at the origin, and I now need to look to the box. What's that angle? 0. Yes, the box is on the root locus. Do you see how we're finding, just with 3 points, what points are on the root locus? Let's now look at the angle of G at the cloud. So now at 3/2, I now need to look from the positive real axis to the cloud. I now need to look from the origin, positive real line, to the cloud. 180. I have 2 180s. So zeros I didn't have any zeros, but do you see if I had zeros you could find the angle from those to those points? Minus 180 plus 180 equals minus 360, which is 0 degrees. That puts me back at 0, which is no, that's not on the root locus. So what's this root locus? I know you're just dying to know. We now know that this piece, that was on the root locus, but since I scratched, it thought I wanted to erase, and I did not. I was just trying to emphasize, and now it destroyed my box. So I apologize, but let me recap what we did. So I can't emphasize too much, but this guy was on. So in fact, this pole goes to the left. This pole goes to the right, and they meet somewhere between. Actually, they meet exactly between each other, which is what? You guys tell me. Where's halfway between 0 and 3/2? Divide 3/2 by 2, 3/4. So now if I can sketch that, and now one goes this way, and one goes that way. Ooh, kind of fun. Now that 3/2 is going to come inside the unit circle. The one at the origin is going to come to the right, and they're going to meet right at 3/4. So there's a gain k, and you can find that gain k when z is equal to 3/4 to get you right there. You crank up the gain a little bit more, and what happens? They go opposite directions, plus and minus 90 degrees, or well, 180 degrees away from each other. And if you crank up the gain too much, what's going to happen relative to the unit circle? It's going to go outside the unit circle. Do you see there's a range of k for stability with 2 poles and no finite zeros? So maybe we'll start next time with some different root locus patterns, but you can now just start dreaming about these root loci, and we'll go from there. Thank you for your patience. Ooh.